Welcome back to the DevOps track, everyone. I'm Justin Warren, your host for today. And our next talk is called Planning for Failure Using Chaos Engineering. And I am pleased to welcome our presenter, Amit Saha. Amit, thank you for presenting here at DevOps. Take it away.
Thank you. Hello, everyone. My name is Amit Saha, and I work for Atlassian as a software engineer. Today, I'll be sharing my learnings and excitement about using chaos engineering techniques to help plan for failure scenarios in software systems. This is the best kind of talk for me because I'm going to fumble a bit, I'm going to stutter a bit, but we'll get there at the end. So yeah, let's get started. Now that you're here, why should you continue listening to me? In the recent past, I worked with teams to assess their production readiness. We are rolling out several new services. We had alerts, we had dashboards, but we wanted to test the various configurations, help team members get familiar with on-call hygiene. So these team members were fairly new to the company. So they may have had prior experience with being on call and for the services, but the tools, the service that we had in-house were quite different from what they were used to before. So we wanted to get them, sort of warming up almost for their on-call schedules. Atlassian had a very well-developed culture around chaos engineering practices. We call it war games internally. And I adopted that as my key strategy for this exercise. And I became a fan of applying chaos engineering techniques for this purpose. And so I want to spread my excitement and share my learnings today. I will start my talk with a hypothesis. And by the end, I'll have made enough points towards proving that hypothesis. And the hypothesis is chaos engineering techniques can help continuously assess your production readiness. But I'll not declare it proved or validated by the end. That's for you to find out for yourself. But I'm positive you will find that's the case. I also like to think of production readiness as failure readiness, since in my head, and probably all of your heads, production is pretty much failure in some shape or form, whether it's 0.01% or whether it's 0.001% or 10%. We have I have divided the talk into 4 key areas. We'll start off with an introduction. We'll then go over organizing chaos engineering experiments. We'll talk a bit about people systems. Then we'll talk about chaos engineering tools. And then finally a summary to really drill down the chaos into all of you. Let's get started. So the best laid plans often go awry. And I have lived in Sydney long enough to see enough of these that the next time I see it, which will be after a pretty long time because of obvious reasons, I will probably be surprised that, okay, yeah, we're back again here. So this is from a new service that was rolled out for those of you who are not from Sydney. This is the Sydney Metro, and which was rolled out with a lot of fanfare after a lot of planning, with sufficient testing for that matter. But within days, we had issues. So we rolled out something into production and we had issues. And that's why we have the train replacement buses, always ready to go. So getting closer to the conference topic, systems fail. We have hardware failures. We have mercurial cores that don't count. So check out this paper called Silent Data Corruption, which is a paper by Facebook and related work by Google, where they found that a task only failed on a specific core. Closer to home, we perhaps don't experience, not most of us experience mercurial cores, but we do experience exhaustion of finite resources. Memory, disk space, CPU cycles, network capacity, we are all too familiar with this. And then we have software failures. Bugs, where we may not have tested a code path properly, where we may not have foreseen something breaking in a way that it broke. And then we have real-world failures, breaking underlying assumptions in software. And then people. During an incident, the on-call person finding out that they don't have the necessary access to deactivate a malicious account. I can bet that a lot among you has actually experienced this. And hence, we put in circuit breakers, we have rate limiters, we have exponential backoffs in retries in our code. We put in redundancy. We want to run more than one copy of our application. We put in disaster recovery plans, and we create runbooks for people to follow. And we also have our fail-safe, which is, okay, if everything else fails, we'll still we'll say put in 4 nines, and if we don't meet those 4 nines, we'll sort of compensate our customer in some way. So we essentially throw money at the problem by signing SLAs. We don't even tell them that, yes, we are going to be 100% off for you. We factor that in. And yet, the next incident happens and catches us by surprise. Alerts didn't fire, autoscaling didn't happen, with a question mark. I thought we had circuit breakers. Oh, and we just had a SLO breach. And if you had any doubts about which PyCon AU track you're in the DevOps track. So what can you do? We can borrow some ideas from the scientific method. The scientific method essentially is it's a process, an ongoing process where we ask questions, we research an area, we form a hypothesis, we test that hypothesis with experiments, we analyze the data, we report conclusions, come up with action items, and then we rinse and repeat. So we are going to put our science hat on, and we're going to learn how we can organize chaos engineering experiments. The basic idea is we want to intentionally break our systems under controlled conditions. We break the carefully orchestrated mix of sync and async workflows and verify the guardrails. What do we break? We break our finite resources, exhaust the CPU, exhaust the memory, exhaust file descriptors. We test the network capacity at different levels. We think about breaking our dependencies, our libraries, our services, the data stores that our application depends on, and any resource your software really depends on. Your logging, your monitoring, your APM, the application monitoring management agents. I believe I got that abbreviation correct. So anything that you're running on the system and your application is talking to directly should be a potential fault injection point. So it's really becoming curious about your system and becoming the bad actor and thinking of ways you can break it. So for example, let's say you have implemented asynchronous workflow in your application and introduced timeout, which is longer than your polling duration. Does your app keep polling forever? Let's say you have webhooks in your application, receive the webhook correctly, but drop the payload. What happens? Does something tell you that something like this has happened, or you are basically left scratching your heads thinking, what's going on? And a final example, let's say you have enabled, you are using WSGI applications, you're using something like Unicorn or UWSGI, you have enabled worker recycling behavior, and you have been careful enough to set up a jitter so that your workers don't restart don't all restart at the same time. Test that. Send traffic to your service at an expected request per second. How does the worker recycling behavior manifest? With that RPS, are there enough workers there to serve requests when the others are recycling? Are those sufficient? Kill a worker periodically. See what happens. A formal chaos engineering experiment consists of 4 key steps. You start off with a steady state hypothesis. Then you have the fault injection phase. Then you verify the hypothesis that you started off in step 1. And then you identify action items. And then you sort of rinse and repeat. As an example, let's say you have two services, service 1 and service 2. And service 1 depends on service 2. So we formulate an hypothesis saying if service 2 does not respond within 300 milliseconds, service 1 is going to return an error within close to 300 milliseconds. It won't be exactly 300 milliseconds because bits and bytes take time to travel. So it'll be close to 300 milliseconds. And then, so that's a hypothesis. And then you inject a fault. You say, I'm going to add a latency of 5 seconds between the service 2 and the database. So the application, I've got the application text here, it should be service 2. So essentially add a latency of 5 seconds between service 2 and database. Did the application return an error after 300 milliseconds? And in this case, the application is service 1. So that's your hypothesis verification phase. Or did it wait longer? And depending on the answer to that question, you come up with action items. If it waited longer, you should check out your timeout configurations and repeat the experiment to ensure that the timeout has actually solved the problem and that it validates your hypothesis. Now, in a more production-like scenario, you would want to verify whether your alerts fired or not as well, telling you that yes, this service 1 is certainly experiencing higher latency. So that's an example. So now there are 3 key steps before you run a chaos engineering experiment. The first and the most important step is to brainstorm the experiment and formulate your hypothesis. That is step 1 from the previous step. What you will really find useful and what you will really need to design good experiments is a very good idea of the system that you are planning to inject faults in. System design and architecture knowledge is essential to come up with interesting experiment ideas, because it's easy to come up with very generic experimental ideas, and those are good places to start. But eventually the biggest bang for your buck almost will come from if you are designing these key experiments. So for example, let's say you have an incident. So that incident could give you a good, that could be your seed to come up with this experiment. Perhaps you could inject the same failure that caused the incident, and for your chaos engineering experiment. So this is really a key step. I will just jump over to the next slide. So now this is how we do planning at Atlassian. Well, I'm just kidding. This is not how we do it. So this is a miniature wargaming, like a picture. But this is roughly what you should. So this is a term. There's a term we use internally called tabletop wargaming. I learned it from a colleague. And what the term means is you get together with the team, your team, or maybe the architect if you have one, maybe the senior engineers in the team, and you sort of brainstorm ideas to break your system. And you do that on a whiteboard, you do that on a table, on a virtual whiteboard these days. And so you lay down all the pieces, you lay down all the dependencies, for example, you lay down the different interactions of your system with your external systems, and then you think about breaking them. So once you have got the experiment, once you have got the hypothesis, the next step is how do you inject those failures? So choose your tools. We will go over a few tools later in the presentation, but sometimes these will be quite custom tools or custom code that you will have to write, maybe perhaps modifying your application in a way to inject those failures. So it will be a mix of both generic tools as well as something custom that you will have to implement for your application. So once you're done with the brainstorming, you have chosen your tools, the third step is schedule a meeting with all the key people. So for example, people who would be on call, the team leads, architects, and typically you'd block around 1.5 hours for conducting the experiment, as well as then coming up with, analyzing the outcomes, validating your hypothesis, coming up with the action items, and just sort of doing like a comparison between expectation and reality. And then you repeat the step again. So it is a fairly time-consuming step. It is because to really get value out of it, you need to devote that time into doing these experiments. The another key, so to sort of have a single person orchestrating all of these, arranging meetings, ensuring that people turn up. What we follow internally is we nominate a person called a Wargame champion who is in charge of coordinating the various logistics associated with the process. Schedule the experiment and then orchestrate the experiment along with the other team members. So this is the person who is driving this whole thing, along with help from everybody else who is involved with the experiment. And of course, you should ensure your failure injection tools and scripts work before the real experiment. The last thing you want is get somebody in a room for 1.5 hours and then figure out that your scripts are not working. There are two other, or perhaps one step that is really vital, is the ability to generate load or traffic for your experiment. Locust, Python community favorite, is great for HTTP services. If you have integration or synthetic tests, they are useful too. The idea is that you need to generate enough traffic so that you can, there's something to break in your application. During the experiment, get everyone in a virtual room. When we are back in office, it can be a single conference room, like with dashboards and notification channels probably up on a giant monitor or screen. And then there's this other aspect is, do you do blind failure injection or do you do predefined fault injection? Blind failure injections are super useful for as a training day exercise where you want to, maybe senior members want to use it as like a tool for training of your junior team members. Or it can be the predefined fault injections where the faults that are going to be introduced are well defined and well communicated before. Another fundamental question is staging or production. The key is you should be able to easily reset your systems to the state that they were before you started the experiment. Start gradually with the staging, and then when you're confident, go for production. And perhaps if you have automated failure injection, you may want it as an opt-out model for staging and an opt-in model for production. Couple of prerequisites. You need to be able to run arbitrary commands or having admin style privileges in your cloud or on-prem account. And you also need to have metrics, dashboards, logs. Otherwise, you don't really know what's going on with your application, and you won't be able to analyze the result of introducing those faults. Great. So people systems. And I've got a hypothetical scenario here. I've got the hypothetical in quotes because it's based on something recently experienced. So we get a on-call, we get a pager, and we see that, okay, we have some spam requests coming in, and the on-call person jumps in. They realize, okay, yeah, let me just deactivate those accounts. And then Jane realizes that, oh, I don't have the right permissions. Let me get this other person. And that person also doesn't have the right permissions. And then eventually we get this person who has the right access, and then they start deactivating the accounts. That's why we need to treat our people and the steps where people are involved as systems as well. We need to practice, we need to inject a bit of chaos into our people systems as well. There's this talk called Chaos Engineering for People Systems by Dave Renson from Google, who talks about companies being distributed systems. And they share some ideas around how you could perform chaos engineering experiments for people. So things like do a staycation where 50% of the normal usual staff will just say, okay, no, we are not present, and let everybody else handle any failure, any incident that comes up. The book Release It, chapter 17, talks about zombie apocalypse. Simulating a zombie apocalypse where again, the same idea is make some of your people not play any role during an incident and see how it goes. And that is why it's really useful when you are performing this kind of experiments on a staging environment rather than production. Test your playbooks. Test your team and treat it as a team building exercises. Like I have really found it very useful to get everybody together and run this experiment, and they are all working with each other. They're talking out loud, discussing why this could be happening and what can be done about it, and so on and so forth. So it's really great for that too. So a couple of key points to remember. Let people know that you're running a chaos engineering experiment. The last thing you want to happen is people thinking or being woken up at 3 a.m. So that's another thing. You should be mindful of time zones of the key on-call people. You don't want to be waking people up at 3 a.m. because you're running a chaos engineering experiment. That still is from the movie War Games. Yeah, it was great. Okay, the next our section we're going to talk about chaos engineering tools. And there is actually a dearth of tools that you will find, and that is why what I'm going to talk about is only going to be a representative sample. So there is no shortage of tools in the chaos engineering community, but you really need to understand most of these tools probably are using these fundamental tools that I have found so far. IP tables, it's like the duct tape of the internet. I heard somebody say many years back, I think. That you will find like that being used in many tools, underlying tools, which give you a higher level layer. TCP kill, which allows you to break TCP connections. And IP tables allows you to introduce DNS-based sinkholes. It allows you to introduce probable failure scenarios, and so on and so forth. Toxic proxy and TC, which is traffic control, they are super useful to add delay to network traffic. So you can use these tools to intercept traffic and add arbitrary delays. The third program is StressNG, which is really useful for simulating CPU, memory, and I/O stress. So I've got a demo. I'll not do it live. I'll have a recording, so I'll just show it. But I have this two sample services, service 1, service 2, where service 2 is talking to a MySQL database. And they're all running in Docker containers. That repo there has this complete demo that you can run on your own. So what I'm going to do is I'm going to play a video. So I have got So I've got this service is running, and I'm going to run the curl command to make a HTTP request to service 1. And as you can see here, it gets a response. There's this HTML sort of block that I've got here, and it gets a response in about 0.6 seconds, right? Okay, great. So that's a normal default behavior. And I just do it again just to sort of, and then what I do is I inject the fault. So I run this Python script. Yeah, so my fault is injected. So now I'm going to run this script command again. And you can see that it takes longer, 6 seconds. Okay, and now what I'm going to do is I'm going to add this query parameter. So by the way, this is a wrong query parameter that I added, so that's my mistake. So I'm going to add the right query parameter, and then we'll see that yes. So I've got this query parameter. It's like what it's going to do is it's going to add a timeout. So now So now you're going to see that we get the response within 0.3 seconds. Remember, the latency injection is still there, so the delay is still there, but so we get a response, but this is a 500. That's because we have now enforced the timeout on service 1, and so that's why we get a 500 response. Yeah, so that's the demo. So let's go back to our presentation. Yeah, so and then, yes, so I talked about this fundamental tools, and the inject latency script that I have, that uses the TC command or program to inject the latency. Okay, the next tool or software I want to talk about that is really useful is called the Chaos Toolkit, and it allows you to inject various faults using external drivers. So they have inbuilt drivers for AWS, GCP, Kubernetes, Toxi Proxy, and you can write your own driver using Python, which is great. If your service is hosted on AWS, AWS has a service called Fault Injection Simulator, and you can do things like RDS failover. You can trigger errors into the API calls. So for example, you could add a delay to the auto-scaling API calls, and you can think of the interesting experiments you can run using that. What if your auto-scaling activity is delayed by 20 seconds? What happens to your application under load? So, okay, great. So summary. So the whole point of chaos engineering and what it's trying to state is embrace the chaos. It's really about assessing your readiness when your systems fail, because it's not a matter of if your systems fail, it's a matter of when. And often it happens that known failure scenarios may come together to teach you about unknown failure scenarios, emergent properties, because two things may add up to something completely different that you didn't even expect. And that's what we want to get ahead of almost by simulating this using chaos engineering experiments. There's this article on coding horror called Working with Chaos Monkey, and there's this quote from that article. So it begins with this: sometimes you don't get a choice, the chaos monkey chooses you. And it ends with this, which is, that's why, even though it sounds crazy, the best way to avoid failure is to fail constantly. And that is very profound. So there are quite a number of resources on chaos engineering. And I have got 3 resources here because I find these are the these are the 3 resources which really drill down, or at least the first 2 resources. They really talk about the principles, they talk about the ideas. They are not about the tools, which sometimes the software community cannot get enough of. So those are the first 2 resources. So if you are getting started with chaos engineering, if you wanted to learn about chaos engineering and the ideas and the principles, the first 2 resources are the key. The third book is great for hands-on learning. The author has done a great job for using basic tools which you can run on your local system to just play and familiarize yourself with the ideas of chaos engineering. Great. Thanks everybody who chose my talk today over the other tracks. Thanks to all the organizers who have pulled this conference in these circumstances. It's just great. Thanks to all the Next Day Video folks I have had a chance to interact with. They have been super helpful, super friendly, super nice people. I'm contactable at Icorand on Twitter. You can email me. I've got the talk materials on my GitHub repo, and I have a website at icorand.me. I will not take questions now, but I'm happy to answer any in the chat or later on. So great, thank you everyone.
Awesome, thanks Amit. That was amazing. Lots of really cool resources in there. There's a few there that I haven't seen, so I'm keen to go and look those up. This kind of stuff of dealing with failure by embracing the chaos, as you put it, is close to my heart. So I look forward to digging into those. Yes. So as Amit said, we're right up on time. So the questions that are there, and there are some there already for you, Amit. If you've got any more, just raise them in the chat or chuck them into the questions. Amit will be around to answer them. And with that, we're now on a break for lunch. So do get up, leave the computer, have some water after the questions, of course. Grab some food, re-energize yourselves. We are back as a conference. We're back at about, let me check my notes. I think it's about 1:30. Yes, lunch break is until 1:30. This track doesn't have a talk until 2:15 though. So you will have a chance to go and explore some of the other tracks, and I encourage you to do so. But be back here at 2:15 p.m. When we have a talk by Peter Chu. Things might go wrong in a data-intensive application. Until then, enjoy lunch, enjoy the questions, enjoy the conference, and we'll see you back.